start with some overview of some basic concepts involving Lie groups, algebra and representations and so on. And towards the end, this course of lectures will visually discuss some elements of topology and so on, as I have been doing. But first we'll do a bit of okay. So today what I will do, so first of all let me tell you the books that I would refer to off and on. There's a book by Humphreys. It's called Lie algebra and this representation of something. And then there's a so this is a mathematical book, and there's also a book by Gordon Rajan. There's an even more mathematical book, Gordon Rajan, and then there are two books, Kahn and Georgia. Kahn also is something like algebra and representation or something. Georgia explicitly says that it's group theory for particle bricks. So no pretenses there. And then there's another book which has quite a bit of finite groups which you may or may not like, but if you really want to learn group theory in some good detail, then you have to learn that stuff. So this is a sort of bigger book than these two. These two are small, and so on. Okay, I'll mention more books if I use them. It's not that I'm going to use all of them. Okay, so let me start with some overview. Today we will discuss some examples of groups and subgroups, group isomorphism, representations, and reducible representations, and so on, and a bit of finite groups and etc. if time permits. Let me begin. Let me begin with the simplest example that you can imagine. That is that take three-dimensional vector point in R3 and consider the set of linear transformations which is a matrix acting on this vector x with the condition that the norm of x prime has to be the same as the norm of x. So everybody knows what the norm of x is. So the norm of x is x1 squared plus x2. So the norm of x squared is this. So clearly this condition implies the following for the matrix R. Okay, so if you write these things in terms of column vectors, so this object will give you x, x, and x for all x. Therefore, you must have R identity. these are called optimal matrices. So I claim that the set of such linear transformations is a group. Okay. So in order to say that, I have to say what a group is. And then we'll come back to this and show that it's a group. Many of you already know what I'm going to say in the first half an hour. So you can go to sleep. Okay, group. So now group is a set G which comes with a map which takes two elements of G and sends it to one element of G. Okay? So you have two. So I'll use maps between sets as a single arrow like that, and maps between elements as an arrow with a cut like this. So this, I think in tech is called maps. Okay, so this object, this has a name. I'll call it G1.G2, but there could be circumstances in which this multiplication, okay, so this is called group multiplication. Group multiplication. This is an abstract concept. So depending on the situation, I could even define addition as a group multiplication. Okay. So for example, the real line could be identified as an additive. It is group multiplication, so to say multiplication could be an addition. All I need is that it should take two elements of this set and send it to one. Whether I call it as dot or plus or whatever it is. Okay? Good. So this would be called a group, provided this is called a group. Okay. Provided a group multiplication satisfies the following properties. So number one is that there should be a special element which are called identity such that whether I multiply G on the right by identity or on the left by identity, I should get back G. Since I am writing this separately, you can imagine that I am considering the general case in which the multiplication is not commutative. Okay. So generically, multiplication will not be commutative. Okay. So commutative groups are also called abelian groups. The concept is clear. G1, G2 should be the same as G1, but generically we would be present. Okay. And then so this is called identity. So E is called identity. And then the existence of an inverse. There should be an element, let me call it G prime, with a property. Multiplying by G prime on the right or on the left should give you identity. This is called an inverse and denoted by a special name, G inverse. Okay, so that's that. And then there should be the so-called associative property. So that is to say, for all, so here I mean this of course for all G. Okay, so for all G. This symbol, this the turned around capital E is called there exists. Okay. And now and this is for all. These are just some abbreviations which make my.
So,
Yes.
well, by for all G you mean for all G in capital G?
Yes, yes. Thank you. For all G in capital G, such things should happen. And this property says that brackets can be removed. G1, G2, G3 is the same thing whether you do the grouping this way or that way. This is called the associativity property. Okay, so now I claim that the set of these linear transformations is a group. So by the way, when I write it this way, then the closure is not mentioned separately, because I am saying that for all G1, G2, this thing belongs to G. So this is called closure. Okay? Okay. Now, much of these properties follow for these guys, because matrix multiplications have this property. There is identity. The identity clearly satisfies this, no doubt. So the set of R. So now what I'm going to say is that the set of R, okay, is a group G with these properties. Okay. This is matrix inverse. Why does R have an inverse? Because from here you can find that determinant of R whole square is equal to 1. So therefore determinant of R can be plus 1 or minus 1. Therefore it cannot be 0. So therefore it has an inverse. Okay. So it has an inverse. It has an identity, because identity satisfies trivial with this property. And associativity just follows from associativity property of matrices. Okay. All I need to check is that closure satisfies. Okay, is satisfied. How does that work? So that is also simple. That suppose there are two such R matrices, R1 and R2, each satisfying this is equal to 1 and this is equal to 2. Clearly I define the combined element by matrix multiplication, so therefore this should satisfy the identity, but that of course follows because this is R2 G, R1 G, R1 R. This is equal to 1. This is equal to 1, so that everything follows. Okay, so therefore, so if a group is defined in terms of matrices, okay, so this later on we will identify this with what is called defining representation. Okay. So this group O3 is an important group. It will keep appearing in various instances. But if a group is defined in terms of matrices, okay, then some of these things are quite obvious. Okay. This you have to work a little bit. Associativity, these things are quite obvious. So you might have thought that, why go through all this song and dance, because some of these properties are obvious. Okay. Just to make the point, let me give you an example of abstract groups which are defined just by the group multiplication technique. Then it's not so. Then these are very non-trivial properties. Okay. So what I mean to say is the following. Let me just give you example examples of finite groups in which we will define the group by a group multiplication. Okay, what do I mean? Let us say that I want to construct a set of two elements. A set of two elements, and I want to define a group from them. Okay, so I'm going to define the number of elements in a finite group as what is called as order. Okay. So a group of order 2, I'm going to construct that. Okay. So now, so at least two of these will be used for sure. So one has to be E. Okay. The other one will call A. And what am I doing? I'm giving you this map in the form of a table. This is called the table, multiplication table. Okay, let's start filling out if we can. What is this? So here the notation is that it's this thing times that is what comes in here. Okay. So what should be here? E. What should be here? A. What should be here? A. Now what should be here? E. Why? So this is the why not A?
Because that would imply A is E.
Inverse of A. Inverse of A should be something between these. Now inverse of A could be A or it could be E. Is there anything wrong with having inverse of A equal to E?
Then A itself will be E and then it will be
This will not satisfy this one. If A inverse is, it will not satisfy this one. If A inverse is E, then clearly, so it doesn't work. Now, so this was easy. So this group is called C2. We will have many more things to say about this group. So the simple representation of this group, this whole table is that it's one element A and it has A squared. Okay? So we will have several representations of this in the next class. Now let me give you one more slightly. So now I have a set of 3 elements and I want to form a group out of this by defining a multiplication table. Okay? Now let's go on. So this column is EAB, right? Because it's multiplying E on the right. So it's E, A, B. And this row is also EAB. This is A, B. Now there are 4 unknowns. Yeah? So I leave this as an exercise to you that the only way you can fill this up is by declaring that A squared is equal to B and A cubed is equal to E. And this object is called C3. This is the only group of orders, and here you actually have to look at all the properties. Okay? Something or the other you will violate if you just try to put in arbitrary 4 elements here. Just put 4 elements arbitrarily in this. Okay? You won't satisfy all 3 of us. Okay? So it's non-trivial. Okay? So these properties are non-trivial, and so this is the problem. This is. Please do these problems. These will reappear as assignment problems. Whoever is editing the course, please take that in mind. Keep that in mind. Okay. All right. So we will do some and if you declare that composition of permutations to be multiplications, then clearly what you have here is another composition. Okay. So we will have some discussions of those groups a little bit only. Yes.
So if we don't use the fact that each element can open only one particular row or column,
Yes.
without using the fact that this is an abelian group from this properties.
Nobody has said it's an abelian group.
So
If it's an abelian group, then
Yes.
the game is over. No, but I have not said it's an abelian group. It turns out to be an abelian group. Okay. So it's
the
some,
group
yeah, you should have some fun with this. And if you have 4 elements, try doing that. There will be 2 groups. Okay. All right. So the book of Hammermesh, okay, does this, hammering. All right. Okay. So that was the first thing. So we defined this group O3 by some invariants. Okay. Now there's some obvious generalization of this way of defining groups. Okay, which is the following. ON. So it's obvious what the definition is. Linear transformations on Rn such that this is true, and such R's will again satisfy RTR identity. This identity is in by n like that, so that's O n. There is also OPQ. That's the same stuff as that, but it's a little funny. Here, x squared will be defined with the first p guys with plus signs and the remaining fellows with minus sign. Does it ring a bell to any of you? O3, 1.
Relativity.
Okay. So that's relativity, and these will have various other these will have various other applications, especially in relativity. Okay, and then of course there are the ISO cousins of these, which I will come to in a moment when I talk about subgroups. Okay, and again the same drill, but when this x is a complex vector. So when x is a complex vector, then and again I'm doing the same thing. It's let me call it u, and now this object. Does everybody know what this norm square is? So here, this is an object like this, x1, x2, xn. Each of these are complex numbers, and I'm supposed to do x1 mod square xn square, and that will correspond to, in terms of the property of matrices, is that u dagger u. Oh, I forgot to say one thing here. This is R transpose u as well as R transpose. Most of these should be equal to identity. And u dagger u dagger, which should a similar generalization to this, you can also talk about UPQ, in which the first P of them has plus signs, and the remaining guys have minus signs. Okay? Alright. Good. Now, as
Is the UPQ relevant to any physical space?
yeah. I mean, they're relevant to many situations, but so in string theory, they're relevant. So the group, U2, 2 is an important group in understanding something called ADS-CFT, etc. Okay, all right. So, but for now we're doing mathematics. Okay, good. So I'll come back to the physics of these things once we are done with the basic mathematical concepts, as I have declared on my initial notice about the concept. Okay, so everybody is okay with the concept of groups. Okay, so we discussed a little bit about what finite groups are, and a little bit about matrix groups. These are all matrix groups because I'm defining them in terms of linear transformations on vector spaces. All right. Now, a subgroup is an easy concept. So, a subgroup. One more definition. Sub. It's a subset of a group which itself is a group. Okay. Subset of a group which itself is a group is a group. That's a subgroup. It's called a subgroup. It's called a subgroup. Now define a subset of O3. So O3 elements. So for example, O3 elements will satisfy determinant of R equal to plus 1. This I claim is a subgroup. Okay, and what do I do to check such a thing? I have to check that this is a group. Okay. So again, much of this goes through because the identity satisfies this. So this is satisfied. Okay. So the O3 elements which satisfy this does contain the identity.
What is determinant R? What is determinant of R means? It's
Determinant
modulus of
R.
R, the magnitude.
No. R is a matrix.
Oh, the rotation. I was confusing with this.
Yeah. So okay, so I'm using here this notation in which R is a matrix.
Okay.
So if you wish, it's like yes. Okay. You can think of this as a linear transformation, as a linear operator on a vector space, or which always has in any particular basis it has a representation in terms of R equals, which is a matrix. Okay, so that determinant is equal to SC. So this again checks out because the identity, okay, satisfies satisfies this one. So this set contains identity. Okay. How about this? Is the inverse included in this one? Clearly it is, because determinant of R inverse, that also is 1, because it's 1 over 1. So the inverse is included. So the determinant of R inverse is equal to 1. This associativity is always a trivial consequence of matrix representation of group. And the closure. Is the closure okay? Because clearly determinant of R1 and R2 is equal to the product of determinants. So that's also okay. So therefore this is a group which is clearly a subset of O3. Okay, therefore this is a group, this is a subgroup, and this is an important group. It's called SO3. Okay, this will identify the group of rotations. Okay. Alright, so question. I could also take the subset with determinant of R equal to -1, because I said that O3 means the determinant of R whole square is equal to 1. So the solutions are +1 or -1. Why didn't I take the Right. So the only choice that I have here is to take determinant of R equal to +1. Okay. Good. So a similar thing, I could do a similar thing with UN, fellows. Okay. So with UN, this condition U dagger U dagger equal to 1 gives me determinant of Q mod squared equal to 1. Right? Therefore, determinant of U is some phase e to the power I eta. Alright? So now I can again take a subset, which is the group. How? Just by saying that e to the power I eta is 1. So eta is equal to 0. And again by the same logic, this is the only possibility that you have. If you took eta to be 30 degrees, it will not work. Okay? So this condition equal to 1 again defines the subgroup and is called SU. Oh, by the way, so this is not only for O3, but it's generally for ON. There's no need to. This is for SON, and that thing is for SU. Alright. Similarly, you could have SOPQ, so SO31, our group, the Lorentz group, and it could have, depending on your taste, it could be SO31 or SO13. Alright, good. So that's what. Now, there's something more, slightly more non-trivial example. Now I'm rubbing this off. Hopefully, everybody remembers to check. Now I claim that O2 is a subgroup of O3. Okay? This involves another concept. So first of all, the subgroup as a subset and group isomorphism. Okay? So let me first say how I go about showing this. So now what I'm discussing is that O2 is a subgroup of O3. You can immediately generalize this to ON minus 1 is a subgroup of ON. Okay. But first let's see how O2 is a subgroup of O3. Let's define the following group elements which look like as follows. O3 matrix. Okay. And ABCD by itself is an O matrix. Okay. So is this this is of course a subset, no doubt, but is it also a subgroup? That I have not shown. Okay. So I claim that H is a subgroup because H is a group. What do I have to do? I have to take two such guys and show that the form remains the same. Right? So, namely, I have to multiply this with another such fellow, and so let me say that I have given it a name. Let me call this a small r, this 2 by 2 matrix. Then I have r. And I multiply this by another 2 by 2 matrix here. What do I get? That's so obvious. Alright, I guess this. Now it's clear. Okay. Because these are these objects. So first of all, I have to I also have to say that this can be an O3 matrix after all. Okay. In other words, I have to show that this G RTR is equal to identity. Okay. Provided ABCD is an O2 matrix. Okay. But that's clear. By this rule now, this will be RTR 0, 0, 1, 0, 0, and RTR of course is identity by the O2 property. So this is done, and you could do it the other way around also, RRT. Okay. So therefore, this is a subset. It's also a subgroup. Okay. You can check that inverse is it's quite obvious. Okay. So, but why do I say that this is O2? Because what is my definition of O2? My definition of O2 is something different. My definition of O2 is in terms of 2 by 2 matrices of this kind. Okay? I start with some two-dimensional vector. So I start with some two-dimensional vector. So this is my definition of O2. That I multiply this by 2 by 2 matrix such that this happens. Now this is a 2 by 2 matrix. And these matrices here are 3 by 3 matrices. So how can I say that this is O2? It certainly doesn't look like it. But of course, they are uniquely specified by some O2 matrix. So the concept here is something called a group isomorphism. Okay. So we found that this H is a group, and this group is in one-to-one correspondence over an isomorphism. So let me write down. Group isomorphism. So it is a one-to-one map between two groups. G maps to the identity of G tilde. Okay, so group isomorphism between G and G. So that's property number 1. And furthermore, if I so this should respect multiplication. So this is normally what you have called. So this should respect, should be compatible with the multiplication in G. Okay. So if you multiply G1 and G2 inside, as if you have mapped them to f of G1 and f of G2 and multiplied this according to the table of G tilde. So whether you do the multiplication according to the table of G or according to the table of G tilde, you will find the same thing. Okay? So that's so this is another property. Here, if I just remove the property of 1 to 1, then this is something called exactly the same property. This is called homomorphism. So, okay, this 1 to 1 here, this is isomorphism. So I'm not going to write that separately. If I delete the 1 to 1 property, so if I just remove this, then this is called homomorphism. Okay. All right. So therefore, clearly there is one subset, okay, of O3, okay, which is O2. Are there any more? Right? Oh no. Yes. O1 of course. Yes, indeed. But I mean, are there any other O2s?
Different position.
I can shift them. I can shift the block. So clearly, elements of this kind, this is 1, 0, 0, 0, 1, 0, like that, and here I have this, where this is this is another subset of elements like this, and then at least one more, which is this stuff.
A0,
B. So this is 1, 0, 0, 0, 0, A, B, C. Okay? These are all related by a trivial change of basis. Right? So more generally, I can do some similarity transformation which affect this change of basis. Okay? And these are all equivalent. Okay?
what is basis here?
Basis here is, okay, so this guy is the same as this guy, provided I relabel this axis here. So you see that how do these guys act? This fellow acts on 1, 0, 0, 0, 1, 0, non-trivially, okay, and 0, 0, 1, trivial, in the sense that this acting on 0, 0, 1 leaves it the same.
So we are not talking in terms of abstract sense when we talk about basis in this thing.
Oh yeah. Now
Change
I'm
of
saying that suppose you shuffle them in such a way that the invariant vector, okay, is now 1, 0, 0. Okay, so this vector I'm calling now 1, 0, 0. I can always do that. Huh? So these are my basis vectors right now. I'll say these things in more detail soon enough. But now I, change my naming so that E3 is being called 001, whatever, okay, and so on. So, sorry, 100. So E3 is now the invariant vector, and now it non-trivially acts on E1 and E2, what used to be called E1 and E2. So in other words, what I'm saying is that this is what I would call the new basis vector, E1 prime. Okay, so in the primed coordinate system, or in the prime axis, okay, it would look like that. Similarly, I have made another shuffling here, okay, in which, but more generally, bases can be moved around, okay, by an orthogonal transformation, and all these are equivalent things. So there is a phrase which is used by physicists particularly, is that how does the O2 sit inside O3? Okay, so this is the meaning.
So we are
When you say that, yeah.
we are specifically talking about matrices now, not just the group.
Yes.
Yeah.
So this is all about matrix groups. Okay. And that's an important point. But yeah, indeed, we are talking about a particular representation.
of the group.
We are talking about the defining representation of O3. Okay, so that's 3 by 3 defining representation of O3, and inside that, so this cannot be the defining representation of O2. However, a defining representation of O2, which is a 2 by 2 matrix, that can sit in various ways inside O3. Okay, so that's this thing. So it's a subgroup, and there's this notion of sitting inside. You might say that, you know, what is this notation? What is this phrase? You know, group 6 inside groups. 6 by. Okay, so it's like that. Now, so with this, let me immediately go into the notion of representation. So this says right away that it is possible to have three-dimensional representations. Okay, so these guys are 3 by 3 matrix representations in which, you know, this column and this row are not doing anything, but nevertheless it is a 3 by 3 matrix representation of O2. Okay, all the elements here are in one-to-one correspondence with the elements of O2. Okay, so you can possibly have a 3 by 3 matrix representation of O2. Okay, it's not confined to having, so like you already know, for angular momentum studies, you can have, you know, 3 by 3 representations of SO3, of course, but you can have 5 by 5, you can have all those fantastic representations which you already know. Okay, so this is the general idea that you can have. That brings us to the issue of group representations. Okay, so let me put it off. Yeah, do stop me if I go too fast, or mention that I'm going too slow in assuming. But you can't mention it this way. All right. Good. So before defining a representation, I have to define a vector space. Okay. So you might think that it's child's play, but there's a little subtlety that I would like to mention. Okay, so what's a vector space? I have it written here, but I'll write it in sort of shortened version. Vector space V. Okay, so I'm defining now a vector space. So it is a set V. Okay, is called a vector space over real numbers or complex numbers, or more generally some notion called a field. Okay, so I'm not going to, you know, sort of elaborate on what this animal is, because for us this field is going to be real or complex. But if you really want to know, read Horstein or read any of this math books. Okay. All right. So vector space over this. call V1 plus V2. Okay. So that's point number one. So there is a map like that which we call vector addition, and there is another notion which is called scalar multiplication. So if there is then it can take one element from this, another element from the vector space, and you can multiply a vector by a real or a complex number, give you another vector space. And it has an identity, that's called 0 this time, has an identity. Example, points on a sphere are a vector space. I expect some objections. Scalar multiplication will not do. Addition will not do. There is no
S3 is-
identity. Sorry?
S3 is
No.
S3 is just
You can no, S3 no, S3 by itself no. The tangent space to S3 is, but what does it mean? Okay, let me say.
when I say S3, I am actually identifying with Z1 square plus Z2 square equal to 1. So with this mapping, that is, I mean, same structure.
No, but the constraint. Okay, so let us see why these are non-trivial things. Okay, so let us say that I take the example of S. This is not a vector space. Okay, so x1 square plus x2 square plus x3 square equals 1, and x1, x3 is in R3. I take two such elements and I see whether addition of them, okay, is again a member like this. Okay, so I take one such guy and I can even take S1. Let's take S1. Right, simpler. So I take two such guys and x1 square plus x2 square 1. So for this vector addition, let me try the vector addition of R2. Okay. So then my new point will be x1 plus. That clearly does not satisfy this. So therefore, S1 is not a vector space. Okay. S2, S3, none of these are vector spaces. Of course, you might, yes.
When I was saying S3, I was actually identifying it with C2. Then I
You can't identify with C2 because S3 is C2 modulus some identification.
Yes, that is
Okay,
it.
so that constraint. So the constraint does not satisfy the vector addition. That's the important. Okay, so S3 is certainly not a vector space. So it's important to. But S3 has something else. Okay, S3 has some other interesting properties
Yes, you do.
that you can multiply two elements of S3. Okay, so you can take. So we will come to that. You can take S3. You have some point here, and you have some point here, and given 2 points, you have a third point. It's a very weird thing. Okay, so you have Mumbai, and you have New York. You can multiply Mumbai by New York, and you can get a third.
What is multiplication?
So what will happen is that we will identify in the next class SU2 as S3 with SU2. So S3, you can invent, okay, this multiplication property on the S3 manifold, okay, and then you can multiply.
This is not the usual vector space.
No, that's something different. It's group property. Okay, so S3 can be be identified with a group, but it cannot be identified with a vector space. Okay. So that's the thing. So S3 is not a vector space. You can try to invent something else. You know, I have taken the inherited addition here. Okay. That need not be the only thing to do. Okay. So you can try. All right.
So while defining a vector space, associativity and additivity is associativity over addition and additivity.
Associativity of addition and all that. Yeah, it shouldn't be. Well, I have to have yes. I have to have. So I have to have B1 plus B2 plus B1 and all right. And distributed property. Thank you. I forgot to say that. That's B1 plus B2 and okay, all right, good. So it should have all these nice properties, and well, yeah. So this vector addition is commutative. Okay. So even if you try to invent some map from a set S cross S to S, okay, to have it satisfy all these properties, okay, is so these definitions which you might think is ultra mathematical, they actually are they actually give you some very substantial information. So as a result, you can show these things that yeah. There are instances in which you would clearly like something to be a vector space. Okay. So for instance, particle moving on a sphere. Okay. If you didn't know about quantum mechanics, etc., so what you have is a phase space. Okay. But you know that something like a wave function would be very good to have. So, but how do you go from this phase space description to a wave function description? Okay. So for that, people have invented an entire discipline called geometric computation. Okay. So, okay, this might be too. I mean, I can explain this later. All right. So, good. So that's the vector space. And linearly independent vectors, the vectors are, some things in which so these are called linearly independent if no non-trivial linear combination of these can be found, which is zero. Okay. In other words, if you find something which vanishes, this necessarily implies that all the lambda are zero. So this property is called linear independence, and a basis is given by basis of E is a set of linearly independent vectors E1 such that any vector this can be making this point precise, real linear combinations of E1 up to En, if this is so, then this vector space is called in-dimensional, in real dimension. Okay, but
So that just comes from the field where is the vector is defined. I mean, is this the fact
oh yeah,
that
yeah,
this is
yeah,
real
yeah, yeah, yeah.
as
So,
it
yeah, yeah. So this object. So here I am saying that I have chosen R. In this definition, I am choosing R. But if I find a set of vectors such that, so basically what I am saying is that, so I'll give you some example. So in case of the complex vector space, the demand on my basis, okay, is this, that any vector can be represented as a complex linear combination of this. So this, plays an important role in Lie algebra theory, okay? Because often you treat these classical Lie algebras like SL2. When a mathematician says SL2, sometimes they don't distinguish between SL, SL2R, SL. I guess most generally is what is called SL2C. Okay, so that's a complex vector space. But there is an important subset of that which is called SL2R. There is another important subset of that which is called SL2C. I am SU2. So these are all various different kinds of real subalgebras. Okay, I'm going way ahead, but let me give you an example. Okay. So this is something that everybody knows. So this n would be called the real dimension in this case, and this n would be called the complex dimension. Okay. So let me take okay. This is some object like this. Two complex numbers. Okay. So I claim that this any such thing belongs to a C-span of 1, 0 and 0.
Sorry to interrupt.
Yes.
When I was saying that you're talking about CP2, complex positive space 2.
Yes.
CP2 is just here.
Yes. Again, it's the same thing. There's a constraint.
So I think CP2, I was thinking this way, that CP2 is a...
No, none of these are. You can take a vector space and you can impose a constraint on this, non-linear constraint. Then that immediately kills the vector space nature. However, if you take R2, okay, and impose a condition y equal to mx, this is a vector space.
Yeah, this is a... Yes.
Okay, this is a vector space. Degree R. Indeed, that's correct. Absolutely. So this thing is a subspace, okay, which is a vector space by itself.
Linear constant should preserve the vector.
Exactly.
Okay, but I was saying, so what about CP2?
No. Anything in which you use quadratic or higher, okay, will not do. Okay, so by the way, how about this? This also looks like linear.
no, this is not.
Pseudo-linear.
Okay. There is some other concept here, it's called affine, okay, in which the origin plays a role. So here, okay, it has to be without the C business. It has to pass through the origin. Why? Because you take two such terms.
The 1 plus 0 in your set.
So, for example, y equal to ms plus c also does not have the additive identity in it. It doesn't have the origin in it. But there is a way of dealing with that C business also, but let me not go into that. So this guy is a vector space, namely R. Okay, it's isomorphic to the real line. Okay, this guy. Okay, it's a linear thing, including the identity. Okay. Yes.
So the basis, the way you define it is always composed of real having 1 0 and 0 and here.
It's coming. It's coming. Okay, so in this way of doing it, it's a two-dimensional space. Agree? But two complex dimensional space. Why? Why? Because this, what do I mean by this? That C1, C2 can be written as C1, 1, 0 plus C2, 0, 1. Right? So I need two basis vectors, and they are linearly independent, and with the help of two basis vectors only, I can write any C1, C2 like that as a linear combination. It's a complex linear combination. However, I demand now, let's say, that I want to write this as a real linear combination of something. Can I do that? I can do that, of course. So what I have to do is to include with this I0, 0, I. Okay?
Sir,
So,
but dimensionality is defined using the number of vectors in the span, right? So
very good. So the complex dimension is different from the real dimension. So whether you are using complex numbers or real numbers, okay, the dimensionality depends on that. So the complex dimension is half of the real dimension. So the real dimension is twice. So how does this work now? With this, so z1 is equal to, so this is x plus x1 plus iy1, right? x2 plus iy2. So what is this? x1 times that 1 0 plus x2 times 0 1 plus y1 times I0 plus y2.
But it's counted differently.
So, sir, does the dimensionality depend on the field over which we define the vector space?
Clearly, because the same object C2, okay, now is being used as R4, right? It requires 4 independent real numbers. So C2, so this shows also that C2 is the same as R. This same meaning
And with respect to vector.
vector space isomorphism. Yes.
So isomorphism means I understood when you said isomorphism group. So we are in vector space and the field which the vector space is defined over.
Yeah.
That is a part of the definition of the vector space. So are these two same vector spaces or different vector spaces? Right?
Okay. So C2 viewed in this fashion is isomorphic. When C2 is viewed as a vector space over R, that is isomorphic. So this definition is not exactly the same definition as x1, x2, y1. I mean, x1, x2, x3, x4 is normally how we would have defined
R4.
Defined R4. Okay. So that would have been x1 1 0 0 0 plus x2 etc. etc. Now I'm saying that you can make a one-to-one map between this representation and this, not with this one. You're right. So when I think of this as a complex vector space, then this cannot be one-to-one map with this guy. Here x1, x2, y1, and y2 appears. All I have to do is to say y1 is equal to x3 and y2 is equal to x4. Right? So therefore there is a real vector space isomorphism between C2 and R. Right? Okay.
sir, I'm still confused. Like,
Yeah.
here the field remains C, but we are just constraining the coefficients to be real. Is that so?
No. I'm saying that let me define C2 as the column vectors with two complex numbers.
Alright.
I'm saying that this can be understood as having 4 basis elements, okay, and a real linear combination. So this particular fellow can be written as real linear combinations of 4 basis elements.
Alright. So the field still remains C.
So
Just
C2
the-
can be no. This C2 here is just a definition.
Alright.
Okay, but I'm saying that this can be viewed as a vector space over R or over C. When I think of this as a vector space over C, this is it. There are 2 basis elements and the dimension is 2. When I think of this as a vector space over R, then the dimension is 4. Okay, and this is how it works. By the way, it's important to realize that in the specification of the basis vectors, See, I am using I here, maybe.
Yeah. So
But that's the only place where I'm going to use I. Okay? I'm not going to use I's here in the linear combination. Okay? So this will play a role in in what we define as SL2R and what we define as SU2, V algebras and so on and so forth. Okay? So we have to, oftentimes you will find commutation relations with I's in them. Okay? And in some context, commutation relations with I's in them, okay, is not good to have. So in mathematics textbooks, typically it will absorb this I in the definition of the generation. I times J1 would be called J1, I times J2 would be called J2, I times J3 would be called J3. So that J1, J2 is not I J3, it's some minus J3 or J1, J2 J3 or whatever, something like that. Alright, okay, so I just wanted to mention this earlier to you. This block is 5 minutes off. Alright, good. Okay, so that's about vector space. And in fact, if you allow for some other fields like okay, good. And then so linear operators on vector spaces. So linear operators on vector spaces are maps, O, such that O acting on B, you can put a bracket here, and that's another vector. Okay, that's another equivalent B. It's called a linear operator provided it satisfies the linearity condition. Okay. And where lambda and mu are elements of that field, okay, whether it's real number or complex numbers and so on, will satisfy this property. And of course, given the basis, since this is an element of the vector space, clearly it can be written as a linear combination of the basis elements. That linear combination is called OIJ, and that's the matrix of the okay. Now we are almost there in defining. So this is called a linear operator. Linear operator. Good. So, and now, so representation. Representation of the group is homomorphism G from G to some group G tilde, which is the G tilde, which is the group of linear operators on vector space. Okay, that's quite a mouthful. So let me explain what this means. Okay. can have a set of operators on a vector space which can be a group, such as linear operators on R2 represented by such things. Sorry, excuse me. Good. These two guys, I claim, is a group, right? So, and this provides a representation of some group that we have already encountered. Z. Okay, why so? So let us see how these things work out. So first of all, with respect to the normal group matrix multiplication, is clearly a group. Okay, so let me give it the suggested name, A tilde, that's the identity, and this is sorry, this is E tilde, this is A tilde, right? So with the property now that there is an inverse for this, which clearly is this, and E is included in the set, so therefore identity is satisfied, blah 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 blah. So this thing is a group of order 2. Okay? And clearly now I claim that this provides a representation of Z2. In what way? The mapping is that E goes to E tilde and A goes to A tilde. The multiplication table of on this side, on Z2, on the abstract side, is just A square equal to E. And of course AE, EA, M equal to E. It's obvious that the tilde satisfies the same thing. Therefore, this is a 2 by 2 representation of Z2. Oh, I should say that the dimensionality of V is called the dimensionality of the representation. This map itself is called the representation. This map T. So in other words, so what we are asking for is that, so what is this homomorphism once more? Homomorphism basically says that D of G1, G2 should be the same as DG1, UG. Of course, if you just take this, that also is a group. Nothing else. Trivially, that's a group, and that forms a representation of any group. Okay, what is the map? E sends G, any group element G, to the identity element. Okay, in the group of operators. This. Okay, so this is called the trivial, no longer representation. It's called the trivial representation. This is triviality.
ISO any two member group is isomorphic to Z2.
So with this multiplication table, that this. So
Any
anything.
two member group will have the same multiplication table.
No. But they have to be operators on a Hilbert space.
No.
Sorry, vector space.
No, what I'm saying is that any two member group is Z2.
Then it has to satisfy S equal to E. Oh, any
No,
group. Yes, indeed. That's right. However, representation is something more.
Yeah, representation.
Z2, the way I defined, is through the group multiplication table only. Okay. But at that time, I didn't talk about any matrix representation. So, for example, you will find it, tough going when you try to find out matrix representation of the permutation. It's not easy at all. Okay. So that will be an exercise. Yes.
So dimension of the number of element in the vector.
Yes.
Everything is mapped to.
Everything is mapped in.
Dimensional representation means what by what matrix.
Isomorphism.
So here, this provides, okay, so let me say this clearly. So this
It's not
provides
one-to-one map.
2 by 2 matrix representation of Z2. This provides one 2 by 2 matrix representation of Z2. Okay? Let me have another one.
Sir,
Yes.
can you just explain why you are calling it a homomorphism and not an isomorphism?
In this case, it is also an isomorphism. Okay?
But,
But sometimes it will happen so that all groups, I mean, it will be many to one.
This one is just
This one is one.
the trivial representation is homomorphism.
The trivial representation, for example, is precisely homomorphism because everybody goes through this thing. It's a very, very many to one. Now, there's another one. 0, 1, and 1, 0, 0, minus 1. So I claim this is also a group. Everybody okay with me? All I have to check is that there is an identity, it's there, and the square of this is equal to 1. Now there's a difference between this and this. This is a very crucial difference between this and this. Which is that this guy moves every vector in R2 to something else. So this fellow, when acting on xy, where does it take it to? Minus x. So the origin is the only fixed point. So the origin is the only fixed vector. On the other hand, if you, of course, this fellow, identity does not do anything to anybody anyway. But take the non-trivial group elements and see what they do. Okay, so it moves everywhere. Okay, so the invariant subspace, okay, is the zero-dimensional subspace, namely the identity, namely 0. Okay. On the other hand, take this guy. Okay, this of course the whole vector space is invariant under this. But how about this one? So here you see this sends xy to what? X comma minus 1. Therefore, if you take y to 0, this is an invariant subspace. Okay? So this is an example of what is called a reducible representation. So here it acts on different, so the subspace which is spanned by 1, 0, so the span, namely the scalar multiples of 1, 0, okay, are invariant under the entire representation group elements. On the other hand, this fellow, this guy, is not. Okay? So there is a non-trivial representation on this, but there is no non-trivial representation of this. More generally, if it so happens that a vector space can be split as a direct sum of two vector subspaces such that the group representation, this B of G guys, acts separately on this, sends B1 to B1 and acts B2 and sends it to B2. Then the matrices all have a block diagonal structure. So more generally, this is what happens. So there is B1, that's a B1. So it behaves like B1 acting on B1, behaves like B2 acting on B2. So this is what is called a completely reducible representation. In general, there could be some fellow here who just says that only one of these need be the invariant subspace. Okay. The other fellow can act on B2 and give you a linear combination. Okay, that's called a reducible representation. This is called a completely reducible representation, but mostly in our course we will have this. So this is called a completely reducible. back to more details. Yes.
This definition is it true for vector spaces or anything? This only true for
No. Anything. So when I try to find, yeah.
definition of dimensionality. The
Oh yeah. Good. So very good. So this is either the complex dimension of V. In that case, it will be called the complex, dimension, the complex dimension of the representation of V, or it's yeah. Okay, that's okay. All right. So I'll sort of go through this thing again next time because this was a bit fast. So I'll go through them this time. If you have some arbitrary representation, there are tricks to find out whether you have got an irreducible representation or not. Okay. So that is to say, sometimes if you make a similarity transformation, it might get all scrambled. It might not look like block diagonal. So just by looking at it, but the point is, something is a reducible representation if you can find basis such that it becomes block diagonal. Okay, but that basis may not how it comes to you. So how do you know whether it's a reducible representation or an irreducible representation? So there are tricks of the trade for that. Okay, so I'll deal with it. So the job of representation theory is to study irreducible representations, because these are the blocks. If you know about them, okay, then adding more and more such blocks is trivial. Okay? Just like in our example of O2, okay, we had 2x2 representation, which was the defining representation of O2, but we just added some 0, 0, 1 and 0, 0, 1, okay, and we got some 3-dimensional representation. So now let me just before closing. Can you give me a 4x4 representation of O2? So now you know the trick. Okay. So there's some A, B, C, D, 0, 0, and A, B. That's it. In fact, the same. So in particular, if it is SO2, this will prove, well, there's nothing SO2 appears. Theta and yeah, in fact, you can
because
you can have a different.
Theta is a group element, right? Can you have different group and theta?
I can shift them, right? So what I'm saying is that if I shift all of these guys by a constant amount, okay, that will be some representation of O2 in this block and some other representation of O2 in this block. That you can have. Okay. So at least this you can certainly have. So alpha plus theta, plus theta, maybe you can have even more clever things. That of course you can have. So more generally, of course, you can have this. Indeed. Okay.
can we do this in the individual element there and
That you can certainly do. Sure. No doubt. That you can certainly do. So you can have a similar transformation of O2 here and keep it here. Okay, and this remains 0, 0, and 0. Okay. And yeah, you can have all that, but you can scramble them more so that these things become non-zero by doing this. Some 4x4 similarity transformation, so that it's completely unrecognizable. Okay, and you might think that it's an irreducible obviously polynomial, okay, will be factorizable in a particular way. Okay,